Our project is a punching bag capacitance accelerometer. Project by Ashton, Donovan, and Dallas.
Me, Don, and Ashton were at the arcade. We're walking around trying to figure out a game to play. We see the punching bag game. And so Ashton's like, dude, I can get a 999, which is the highest score first. Goes up, walks up, boom, hits it. 111. About the lowest score you could possibly get. So we're all like, what's going on? You know, how's this operating? What's going on? So we realize the machine is designed where the punching bag is hanging like a pendulum from the top of the machine. Once punched, it rotates up and hits the top of the machine. Within the punching bag are sensors. And one of the most common sensors within the punching bag is a capacitance accelerometer. So here's a quick picture of the diagram. And on the next slide, we will discuss it, break it down. Capacitance accelerometer is composed of various parts. External frame, which is connected on the bottom to two fixed electrodes or capacitance plates, which are fixed to the sensor, so they move with the sensor frame. And then they're each tied to a connecting wire. On the left, there is the spring with a constant of K connected to a hanging mass, and the hanging mass has a hanging capacitant plate or another electrode. And they're each equally spaced D apart.
On this slide, I'll be explaining how conservation of charge connects motion to the punching bag to an electrical signal in the accelerometer. The main idea starts with the definition of capacitance. Capacitance tells us how much charge can be stored for a certain voltage, which is shown by the equation C equals Q divided by V. We can also rewrite that as Q equals C times V, which helps us show how voltage changes when capacitance changes. Inside the accelerometer, the moving mass forms two capacitors with the fixed outer plates. When the punching bag is hit, the bag accelerates, and because of inertia, the mass shifts compared to the sensor frame. Plates. Since capacitance is also given by C equals area epsilon divided by D, we know it depends on the distance between the plates. If the distance gets smaller, the capacitance increases, and if the distance gets larger, the capacitance decreases. So when the mass moves, one capacitor gets bigger while the other gets smaller. Because these two capacitors act like capacitors in series, they carry the same charge, and the equivalent capacitance is smaller than either individual capacitor, as shown by the series equation at the bottom. This matters because if the charge stays the same and capacitance decreases, then the voltage has to increase. That is how the system starts turning mechanical motion into an electrical signal that we can measure. This slide kind of builds on the first one, showing how conservation of charge is used with Kirchhoff's current law at the middle node, which is labeled VA. The mass acts as a shared middle node between the two capacitors C1 and C2. Because charge cannot be created or destroyed, the charge from one side and the charge from the other side must balance at the node VA. This is why we start with the condition Q1 plus Q2 equals 0. This is the charge balance form of Kirchhoff's current law for the middle node. Next, we define the two capacitances based on the new plate distances. The left capacitor is C1 equals area times epsilon over D minus X. And the right capacitor is C2 equals area times epsilon D plus X. This shows that when the mass shifts by a distance X, one gap gets smaller and the other gap gets larger. When we substitute those capacitance into charge balance equation, it gives us the full node equation at the bottom. And because area and epsilon appears in both the terms, we can just simplify the expression. It's important because it directly connects the voltages to the mechanical movement of the mass or in other words, as the mass moves, the capacitance changes, and the node voltage VA shifts until charge balance is restored.
Now that we have the relationship between KCL and definition of capacitance in this scenario, we can solve for the distance the center plate is moved, defined as the variable x, as shown on the right. Using the force body diagram shown, we use F equals ma, with the only force being the spring given by Hooke's law. We can then plug in the previously found x and prove acceleration to be proportional to voltage at the center plate. And that's all.